research that he did with Alex Reyes when I was a postdoc in his lab at NYU. Right, so the picture of a cortical neuron is a neuron sitting and receiving thousands of excitatory and inhibitory inputs. And what we're typically interested in, through cross-correlation studies or something like that, is what's the effectiveness of one of these inputs of driving this neuron when presented against this barrage of factors. So what I'm going to talk about today is one measurement of the effectiveness of the synaptic input, and then ways that we can modulate the sensitivity of this neuron to that input. So I'm going to be showing you results from an integrated fire neuron. Just to review, it's a single compartment model that integrates its inputs over time, and then there's a threshold. And when it hits that threshold, when the membrane potential hits that threshold, it actions like a fire, and then the membrane potential resets the polarized potential. And I built in a refractory period that's implemented by having a capacity conductor that's pretty strong that activates after every action potential. And I'm in vivo conditions, the cortical neuron, the model neuron is receiving a barrage of background activity. So I'm not going to go into the exact parameters of the background activity, but it's excitatory and inhibitory inputs. And you hold the neuron at about -58, takes a little bit below threshold. And they're designed to mimic what we think are in vivo conditions. So the output of the neuron is going to look something like this. The idea is it's noisy and it's got a high conductance change, something like what you'd see in vivo. And what we're interested in is how do we characterize the sensitivity of this neuron to one particular input. So I'm going to be calling this the special excitatory input or the special input. So the current arising from this neuron is something like the top here. And we're interested in what effect does this have on the output of this neuron. And typically, if you want to measure the effectiveness of this input, you look at the firing rate histogram. So at the top, I've plotted that the current arising from this excitatory input, the special input. And then at the bottom, in the center, there's 100 spike rasters. So this is 100 trials of the neuron receiving random input, except that the special input occurs at the same point at each time. And what I've done at the bottom is bin the spike times relative to when they occurred, relative to the special input. And you can see, the neuron fires at some steady state firing rate, and then when the special input occurs, you see an elevation in firing rate as a result of that particular input here. So typically, if you want to measure the efficacy of this input, you might say, okay, let's look at what the elevation in firing rate above the baseline firing rate is. And let's just take the area of those extra spikes and call that the efficacy of the input. And one problem with using this as a measurement of synaptic strength is that it depends strongly on the state of the postsynaptic neuron. So for example, if the neuron is very hyperpolarized, the neuron's never going to fire. Whereas if the neuron is depolarized in a state like this, you see a very strong effect of this special input. So if you want to use that method, or that definition of characterizing the effectiveness of the synapse, you have to say it's the effectiveness of that synapse when the postsynaptic neuron is in this state. So what I'm going to talk about today is another way of characterizing the effectiveness of the synapse, and hopefully this might be somewhat more independent of the postsynaptic state. And it's still going to depend on the hit rate or the probability of detection of detecting the synapse. So I'm going to be defining the hit rate as the probability of an action potential being fired within 5 milliseconds after the special input is fired. And then I'm going to be also characterizing the postsynaptic state using the false alarm rate. So this is the probability that the neuron fires an action potential in a 5 millisecond window when the special input is absent. All right, so those of you who are familiar with signal detection theory will realize that I'm building up the receiver-operative heuristic curve of the neuron. And so for those of you who don't know, that's the hit rate, or the probability of detection plotted against the false alarm rate, or the probability that the neuron reports the special input is there when the input was not. Now, typically these receiver-operative characteristic curves are drawn assuming that the possible responses are drawn from underlying distributions. And the analogy in this case is where the membrane potential of the neuron might be, without the special input or with the special input. So what I've drawn here is are distributions of where the membrane potential will fall. The probability of where the membrane potential might be against the value of the the value of the action of the membrane potential, without the special input and with the special input. So you can see that there are two distributions. And actually what the neuron, and when you think about receiver-operative characteristic curves, you typically draw a threshold and call one side a hit and one side a false alarm, or sorry, one side miss. And that's kind of what the neuron is doing. Right? It has an action potential threshold, and and the exact relationship between what's on this side of the threshold and when the neuron fires is not straightforward, but I think this is a good analogy. Now, when you trace out the receiver operating characteristic curve, typically what you do is take this threshold and slide it through these distributions, and each point of the threshold is one of those points in the receiver operating characteristic curve. But I can't move the action potential threshold of the neuron. But what I can do is move these distributions relative to the threshold. And I'm going to be doing that. And so what I'm going to show you next, I'm going to trace out the receiver operating characteristic curve by injecting different levels of baseline current into the neuron. And that's going to increase and decrease the baseline firing rate of the neuron. And when I do that, it's essentially shifting these membrane potential distribution curves up and down along the x-axis relative to the threshold. But you can also think of it as holding these membrane potential distributions fixed and shifting this threshold along the x-axis. And when you do that, that traces out the receiver operating characteristic curve. Now, let me just point out at this point that what we're really doing when the neuron moves along this curve, or when we move the neuron along this curve, is changing the strategy that the neuron uses to detect its input. So the neuron is sitting up and to the right. That's equivalent to setting the threshold very low. So so the neuron's going to report that the neuron's going to never or very rarely miss that this special input is there. It's going to report that it's there. But that's at the expense of also reporting that many false alarms. Whereas if the neuron sits down and to the left, that's equivalent to setting the threshold very high. So it's playing it very safe, and it's going to not report many false alarms, but it's also going to miss many of these special inputs when they occur. All right, so what I just said is that moving along this curve is a change in detection strategy. And that's achieved by simply adding simple excitation and simple inhibition to the neuron. Now, what I just wanted to point out at this point is that shunting inhibition acts the same as just straight inhibition. All right, so what I mean by shunting inhibition is activating conductances in the neuronal membrane that have a reverse potential near rest. Right, so this is just changing the overall conductance of the neuron. Now, that has an inhibitory effect on the neuron. So you'll see that when I increase the shunt conductance, in this case I triple the shunt conductance of the neuron, so I triple the lead conductance of the neuron in your case. Both the hit rate and the false alarm rate go down. But when I then again trace out the receiver operating characteristic curve by injecting different levels of current, you see that the curves are essentially identical. So what we're seeing here is that increasing the shunt conductance is moving the neuron along the same receiver operating characteristic curve. It's not really changing the performance of the neuron at detecting this input. It's not really changing the neuron's sensitivity to this input. All right, so what I would propose at this point then is to measure the neuron's sensitivity or measure the neuron's performance at detecting the special input in the area under this receiver operating characteristic curve being traced out. So, a very sensitive neuron, the receiver operating characteristic curve, the FGL detector, it would go up along the y-axis and over to the right, so it never misses one of these special inputs. But a completely random detector would lie along the receiver operating characteristic curve would lie along the diagonal. And that would represent the case where the hit rates equal the false alarm rates all the time. So what I'm going to do now is shift gears a little bit and talk about ways that we can modulate the shape of this receiver operating characteristic curve and the performance of the neuron at detecting this input. All right, so what I just did before was change the conductance of the neuron by increasing shunting inhibition to the neuron. What I'm going to do now is change the conductance of the neuron by increasing the overall, the excitatory and inhibitory rates together. So this is different than the shunting inhibition because along with the changing conductance comes a change in the variance of the input current or a change in the noise coming into the neuron. This is because the excitatory and inhibitory events are discrete events in time, and they're constantly pulling the neuron up and down, bouncing around the average reversal for the two inputs. Okay, so again, this has an inhibitory effect on the neuron. It moves the neuron down into the left in this ROC space. But when we trace out the receiver operating characteristic curves, now we see a change in the shape. So what we're seeing here is that changing the conductance in this way, where it's being changed along with the change in input noise to the neuron, that changes the performance of the neuron at detecting input, or it's modulating the sensitivity of the neuron to this special input. Sorry, I'm walking. All right, so just to drive that point home, what I did when I changed the shunt conductance, so these are little cartoons of what the synaptic input against time looks like. When I just changed the shunt conductance, the overall conductance went from a low state to a high state, but the variance of the conductance stayed about the same, stayed the same. In this case, what I did was change both the overall level of conductance, but also the variance of the conductance coming into the neuron, or the variance of the input current coming into the neuron. So the real thing the real element that's crucial for changing the sensitivity of the neuron is this increase in input noise. All right, so just to drive that point home, what I'm going to show you now is what happens if I introduce correlations into this barrage of background activity. So the special input is going to stay the same, but now these background inputs are going to be correlated. So this is effectively holding the conductance of the neuron constant, but increasing the input noise coming into the neuron. All right, so that has an excitatory effect, which means that the neuron's going to move to the right. But when we trace out the receiver operating characteristic curves, now again we see a change in the performance. So I brought this example up just to show that another way, to show you that another way of changing the performance of the neuron is changing the correlations in the background activity coming into the neuron. Okay. To sum up, I'm on time, so I'm going to sum up now. All right, so what I've been proposing is that we measure the effectiveness of a synapse by measuring the area under one of these receiver operating characteristic curves of the neuron. And then what I've shown you are two ways that we can change the probability of detection of the neuron. So to illustrate this, what I've done on the left is plot the spike rasters for neurons sitting at this state on the receiver operating characteristic curve. And you can see the baseline firing rate or the false alarm rate and also the probability of detection of the neuron and the firing rate histogram, which is at the bottom. Now, one way of changing the probability of detection is to move the neuron along the receiver operating characteristic curve. So if you look at the right, this represents what the neuron's response is at the green dot on the receiver operating characteristic curve. And you see there's an increase in detection rate that comes along with an increase in false alarm rate. And so this is one way of changing the probability of detection, and you can get this by just increasing excitation or just increasing inhibition, but it's not a change in the sensitivity of the neuron. There's a trade-off between false alarm and probability of detection. Now, if on the other hand we change the shape of the receiver operating characteristic curve, we can get a change in the sensitivity, we can get a change in the probability of detection without the corresponding change in false alarm rate. And this is changing the sensitivity or the performance of the neuron detecting this input. And it can be achieved by either increasing the overall level of background input coming into the neuron or introducing correlations into the background inputs, anything that changes the input noise to the neuron. Okay, thank you very much.
We have time for a couple of questions.
I'm a little bit confused about which result you actually found. That by increasing the balance of excitation inhibition, you're essentially adding a lot of noise at the cell body, and yet the detectability of the remote input is increased under those circumstances?
Decreased. Sorry, so to go from blue to red, I decreased it. I flipped it off. Sorry.
Oh.
Sorry. Yes.
You're kind of saying a way to modulate the effectiveness of a synapse is to do thing one or thing two, but both of those things reduce the effectiveness of the synapse, which is the same to increase the noise and increase the correlation. So are you trying to are you conjecturing that this is that these modulations are actually used to decrease the effectiveness of synapses, or that the network is actually one of the means of increasing the effectiveness of synapses is to quiet the network down and destroy any correlation or anything like that?
All right, so I was trying to draw a distinction between the effectiveness of synapse and just the efficacy. That synapse causes an activation. And I forgot what I was going to say. So, all right, and then I was saying